Inside the heart of a dying star, a crisis unfolds in less than a billionth of a second. 3 helium nuclei, called alpha particles, must fuse together, but the laws of physics say this should be nearly impossible. For decades, it was a fatal flaw in our understanding of how the universe builds carbon. Then a stubborn astronomer named Fred Hoyle made a wild prediction. He insisted the universe had pre-installed a quantum shortcut, a precise energy level that made this fusion possible. He called it a resonance. When they found it, it was tuned to a precision of 1 part in 1 quadrillion, a dial set perfectly so life could ignite. That single, perfect resonance is why you are here to consider it. But carbon is just 1 atom in the periodic table. What about the rest of the cosmic machinery? How many other impossibly perfect settings are hiding in the equations that define everything? Last chapter, we saw how a single nuclear resonance tuned to 1 part in a quadrillion allowed carbon to exist. But that was 1 dial, 1 setting. The question we're left with is how many others are out there. The answer is both more impressive and more unsettling than you might expect. For decades, physicists have been building what may be the most accurate scientific theory ever constructed. It's called the Standard Model. It describes the fundamental particles that make up everything you've ever touched, and 3 of the 4 forces that govern their behavior. Its track record is staggering. In the 1960s, the theory predicted the existence of particles called W and Z bosons with precise masses. Decades later, scientists built a machine the size of a city and found them exactly where the math said they'd be. In 2012, a similar dance played out with the Higgs boson, a particle theorized nearly half a century before it was discovered. The Standard Model doesn't just describe reality, it tells reality what to do. And reality obeys. But here is where the unease begins. The Standard Model does not predict everything from first principles. Buried in its equations are at least 19 numbers that the theory simply requires. The mass of the electron, the strength of the strong nuclear force, the exact coupling constants that determine how particles interact. None of these values emerge from the theory itself. They are measured from the real world and plugged in by hand, like 19 dials on a cosmic control panel that someone had to set before any of this could work. If you want to explore that mystery more deeply, there's an ebook called The Physics of the Divine that examines whether those dials point toward a designer or something else entirely. It's linked in the description below if you're curious. Here's what should keep you up at night. The Standard Model is the best description of nature we have. It works, and yet it doesn't know why its own numbers are what they are. 19 constants, none predicted, all precisely calibrated for a universe where stars burn, carbon forms, and you exist to wonder about it. Why does our most complete theory of reality depend on 19 numbers it cannot explain? The mass difference between an up quark and a down quark is roughly 2 megaelectronvolts. That number is easy to dismiss, but it determines whether the universe contains hydrogen at all. If the down quark were slightly lighter than it is, protons would become heavier than neutrons. Hydrogen atoms would be unstable. Stars would never ignite. Nothing would burn. Consider what that means. Every galaxy, every star, every rocky world in the observable universe exists because of a 2 megaelectronvolt whisper between 2 particles that no one has ever seen directly. Paul Dirac stumbled onto a parallel unease in the 1930s. He was working through the fundamental constants at his desk in Cambridge, scribbling ratios between the forces of nature, when he encountered a number that genuinely disturbed him. Electromagnetism compared to gravity produced a ratio with 40 zeros after the decimal point. Not elegant, not purposeful. A raw, naked coincidence that seemed to mean something no one could articulate. Dirac despised coincidences in physics. He proposed what he called the large number hypothesis, the idea that such an extreme ratio could not be accidental, that the fundamental constants must be changing over time, drifting slowly across the age of the universe. Physicists tested this for decades. They examined ancient light from quasars billions of light years away, the oldest light they could measure, searching for any drift in the fine structure constant, the number that governs how light couples to matter. They found nothing. 137.036. Then, now, across billions of years, identical, and here is why that number matters so deeply. The fine structure constant sits in a range so narrow it defies casual explanation. Shift it 4% higher, and carbon atoms cannot form inside dying stars. Shift it 0.5% lower, and nuclear fusion fails before producing enough energy to sustain itself. 0.5% is the entire margin between a cosmos of stars and a cosmos of cold, dark gas. The up quark and down quark, the fine structure constant, these are not grand forces or spectacular cosmic events. They are the quiet, invisible settings buried beneath every atom you have ever touched. And they are exact. If atoms rest on numbers this precise, what happens when we look at the forces that bind them together? 2%, that is the margin. Imagine the strong nuclear force as a dial you cannot see, built into the foundation of every atom. If someone turned it 2% higher, every pair of protons in the early universe would have fused into something called a diproton, an unstable configuration that decays almost instantly. In those first 3 minutes after the Big Bang, every proton would have found a partner, burned through all available hydrogen, and the universe would have been left with helium and iron. No hydrogen, no water, no stars long-lived enough for planets. Turn that same dial 5% weaker, and the strong force cannot hold a nucleus together beyond a single proton. Hydrogen exists, but nothing else forms. No carbon, no oxygen. A universe of lonely protons, unable to connect. In the 1930s, a Japanese physicist named Hideki Yukawa proposed that something must mediate the force inside the nucleus. He predicted a particle heavier than an electron but lighter than a proton, a messenger shuttling between nucleons. The intuition was correct. The strong force operates at distances so small that 10 trillion of them could fit across a single atom, powerful enough to overcome the violent repulsion between positively charged protons and hold them together in the same nucleus. But strength alone is not enough. The weak nuclear force governs whether a neutron becomes a proton or vice versa, determining the entire ratio of elements produced in the first seconds after the Big Bang. Too fast and protons vanish. Too slow and helium never forms. Without the weak force, the furnace at the heart of every star would never ignite. Then gravity. Relative to electromagnetism, gravity is absurdly feeble, a ratio so extreme that if electromagnetism were set to 1, gravity would be 1/10,000 billion times weaker. That weakness is the point. If gravity were stronger, it would collapse atoms. Weaker, and planets could never coalesce from dust. Every rocky world, every living cell depends on gravity being precisely, stubbornly weak. The standard model contains 19 free parameters, 19 numbers the theory does not predict. It simply accepts them, as though reading them off a blueprint someone else drew. We have looked at quark masses, at the forces that bind nuclei. But there is a deeper question waiting, one that makes all of this look small. What about the rate at which the universe itself is expanding? One number, that is all it takes. Physicists call it the cosmological constant, a single value sitting quietly in Einstein's equations, and it controls whether the universe expands forever or collapses back on itself. We measured it, we know what it is. And the gap between what we measured and what our best theory predicts is not a small error. It is 120 orders of magnitude, a 1 followed by 119 zeros. If that gap were a book, it would not fit in this universe. It would not fit in a trillion universes stacked end to end. In the late 1990s, 2 teams of astronomers were mapping distant supernovae, trying to figure out how fast the universe was slowing down. They expected the answer. Gravity pulls things together. The expansion should be decelerating, the brakes applied by all the matter in the cosmos. Instead, they found the opposite. The expansion was accelerating. Something was pushing outward, something relentless, and when they traced it back to its source, it came from nowhere, empty space itself. The vacuum, nothing. The nothing was doing something. The nothing had energy. This is where the confusion begins. Quantum field theory, the most precise framework humans have ever built, predicts that empty space should seethe with virtual particles, flickering in and out of existence so fast you cannot measure them. The energy density of all that seething should be enormous, not just large. Theorists calculated it and expected a number that would tear galaxies apart within the first instant of cosmic time. What they found instead was a number so small, so vanishingly close to zero, that it defies explanation. The measured value is not just smaller than the prediction. It is smaller by a factor that has no comfortable analogy in any other branch of physics. It is as if you predicted a skyscraper and found a bacterium, then stood there, staring, trying to understand what went wrong with reality itself. If the cosmological constant were even slightly larger, space would stretch so fast that matter could never clump together. No galaxies, no stars, no planets, just an accelerating void cooling into permanent emptiness. But it is not large, it is not zero, which would be strange enough. It sits at a value that permits galaxies to form, permits stars to burn for billions of years, permits the slow accumulation of heavy elements that eventually become carbon, oxygen, iron. It sits at exactly the value required for a life-permitting universe, a coincidence so precise it borders on the absurd. Some physicists, desperate for an explanation, propose the multiverse. Perhaps there are countless universes, each with a different cosmological constant, and we simply find ourselves in the one that allows us to exist. But that is not an explanation. That is a surrender dressed as a theory. It tells us nothing about why the constants take the values they do. It only tells us that if they did not, we would not be here to ask. So we are left with a number, one that controls the fate of everything that exists, and we have no idea why it is what it is. The standard model contains 19 free parameters. This is the most extreme among them, and it points to something we do not understand. Is it a clue we have not yet decoded? An accident too improbable to be real? Or is it something else entirely, something that demands a reason beyond blind chance? We do not know, and the not knowing at this scale should keep you up at night. A man stares at a scrap of paper. The year is 1953, and the calculation in front of him should be impossible. He has taken the measured strength of the strong nuclear force, the glue that holds atomic nuclei together, and he has varied it by just a few percent in his equations. If he increases it slightly, protons fuse too readily. Every star in the cosmos burns through its hydrogen in a flash long before planets can form. If he decreases it even a little, the fuse never lights. Stars never ignite at all. Helium never becomes carbon, and the chemistry of life never begins. The paper in his hands proves the universe is balanced on a razor's edge, but who or what balanced it? This is the problem the weak anthropic principle attempts to solve, and it does so with breathtaking simplicity. It states that we observe a life-permitting universe because we exist to observe it. It is a filter built from our own presence. We cannot find ourselves in a universe that forbids our existence. The conditions must be compatible with our emergence, or we would not be here to note them. On its face, it seems almost logical. It is the ultimate selection effect, but listen to the sound it makes when you tap it. Does it explain why the razor's edge exists at all? No, it only explains why we are on this side of it. Imagine waking up before a firing squad, only to find every rifle has missed. You could say, of course they missed. I am alive to tell the tale. But that does nothing to explain the miracle of every shot going wide. It offers no cause for the staggering odds. It is an observation masquerading as an explanation, a tautology dressed in scientific clothing. Fred Hoyle, the very man who stared at those nuclear calculations, was so unnerved by this precision that he reached a different kind of conclusion. He abandoned the comfortable ground of impersonal chance. A common-sense interpretation of the facts suggests that a superintellect has monkeyed with physics, he said, as well as chemistry and biology. He was not speaking theologically. He was speaking as a mathematician staring at numbers that seemed to scream of intention. The design inference does not dodge the question. It answers it directly, and in doing so, it asks something even more profound. If the universe is engineered, what does that imply about the engineer? So we are left holding two very different tools. One is the anthropic principle, a mirror that reflects our own existence back at us, leaving the mystery untouched behind our reflection. The other is the suggestion of design, a key that promises to open a door but forces us to confront the nature of the locksmith. Does the anthropic principle resolve the tension between the impossible odds and our presence, or does it merely restate the paradox in a quieter voice? The answer depends on whether you believe a mirror can illuminate the room it hangs in. Imagine a watch found on an empty beach. Every gear meshes perfectly. Every spring is calibrated to a tension that keeps time across centuries. You would not say the ocean made it. You would look for a watchmaker. Now consider the alternative. What if, before the watch was ever found, there were an infinite ocean of randomly assembled gears and springs, and most of them produced nothing but scrap metal? The watch on the beach is still remarkable, but its existence becomes a matter of probability, not necessarily of a single, deliberate act. This is the core of the debate that follows from the fine-tuning we've seen. The design inference is a logical step, not a theological one. When you find that 19 independent parameters in the standard model of particle physics, the mass of the Higgs boson, the strength of gravity, the charge of the electron, all require precise calibration within unimaginably narrow ranges to permit a stable universe, the simplest explanation, some argue, is intentional calibration. It's like finding a combination lock where every single tumbler must click into place for the door to open. The inference to design doesn't require faith. It requires the application of our normal, everyday reasoning about complex, specified information to the cosmos itself. But here is where the tension sharpens. The inference can be challenged, and it is. One major counterpoint is the multiverse hypothesis. It suggests our universe isn't the only one. There may be a vast or infinite ensemble of universes, each with its own random set of parameters. Most are sterile, violent, or too fleeting to matter. We simply find ourselves in the one that, by chance, allows for our existence. The watch on the beach is no longer unique. It's the only one you'd ever find, because all the broken ones sink without a trace. Others propose that our current understanding of physics is incomplete. There may be a deeper, undiscovered principle that necessitates these specific values, making them the only possibility, not one choice among many. The watch's gears wouldn't be arbitrary. They'd be the inevitable shape of time itself once you understood the true laws of mechanics. And then there's the stark possibility of selection bias, a direct extension of the anthropic principle we discussed. We can only observe a universe compatible with our existence, so we shouldn't be surprised to find ourselves in one, even if its properties are astronomically unlikely. Physicists like John Wheeler pushed this further with his concept of a participatory universe, suggesting that consciousness isn't just a bystander, but is somehow woven into the act of creation itself. Stephen Hawking flirted with a similar radical idea in his top-down cosmology, where the universe doesn't have a single, fixed history, but a superposition of all possible histories, and we, the observers, help select which one becomes real by measuring it. These ideas don't resolve the question, they deepen it, implying that the relationship between mind and cosmos is far more intimate than we imagined. So we are left standing at a crossroads of interpretation. The evidence of precise fine-tuning is a fact, but it points in multiple directions at once, toward a deliberate architect, toward a blind statistical landscape of countless worlds, toward hidden laws we haven't yet conceived, or toward a fundamental connection between observation and reality. The mystery hasn't been solved. It has simply been made more profound, leaving us suspended between the startling possibility of design and the dizzying possibility of an infinite, indifferent cosmos. There is a particular feeling that settles in when you have been walking through unfamiliar terrain for a long time. Not fear, not confusion, something quieter, a recognition that the ground beneath your feet is real, but the map you started with has been torn to pieces. We began this journey with carbon, a single element in a single star, fusing at a precise resonance that should not exist according to our equations, and yet it does. Every breath you take is proof of that improbable nuclear accident. From there, the layers peeled back. The strong nuclear force, calibrated within a razor-thin margin so that protons hold together without flying apart. The weak force, balanced so that stars burn slowly enough for chemistry to unfold over billions of years. The electromagnetic force, tuned to permit atoms, molecules, and eventually neural tissue. Each constant we examined was another thread in a fabric of extraordinary precision. And then we arrived at the Standard Model itself, physicists' most successful theory. It predicts the behavior of particles with staggering accuracy, parts in a trillion. It has passed every experimental test we have thrown at it. And yet it carries 19 free parameters, 19 numbers plugged in by hand, measured from experiment, not derived from any deeper principle. Why does the electron have the mass it does? Why is the strong coupling constant what it is? The theory does not say. It simply takes the numbers and works. But the Standard Model, for all its brilliance, is not complete. It does not include gravity. It does not account for dark matter, which makes up roughly 85% of all the mass in the universe. It does not reconcile with general relativity at the smallest scales. There is no quantum theory of everything. The most accurate map of reality we have is missing enormous territories. And in that incompleteness lives what we might call a God-shaped hole, not a theological claim, a structural one. The parameters that make life possible are unexplained. No experiment has hinted at a deeper theory that would predict them. No symmetry demands that the cosmological constant be what it is. We have measured these numbers with extraordinary precision. We have not explained them. This is where honest physics leaves us. Standing at the edge of what we know, looking out into a darkness that is not empty but full of questions. The universe appears fine-tuned for life. Whether that tuning implies a tuner, a mind, a purpose, a deliberate act, remains the deepest open question in science. Not because the evidence is hidden, but because the evidence genuinely points in more than one direction at once. And perhaps that is the most truthful place we could possibly stand. Thank you for walking this path with me. And yet, those 19 numbers remain. They are not footnotes in a textbook. They are the universe's master tuning fork, struck once and vibrating ever since. The Standard Model is a perfect description of what happens when those numbers are set. It is utterly silent on why they are set at all, has haunted physics for a century. It sits at the intersection of evidence and meaning. For anyone who wants to walk that intersection, to see how cosmological constants, the anthropic principle, and ancient philosophical questions collide, there is a guide. It is called The Physics of the Divine. Exploring fine-tuning, consciousness, and the quest for God. It explores whether this tuning points to a designer, or to a multiverse, or to something else entirely. You can find a link in the description. Perhaps the most honest answer is that we don't know, and that the not knowing is where the real journey begins.